Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And today we're going to be talking about balance and imbalance of forces, diffluence and divergence. Does the one necessarily mean the other? And does confluence mean convergence? Does one necessarily mean the other? No, it doesn't. And so we're going to talk about all of that coming up right now. So let me go on ahead and miniaturize myself. And we're going to start off with this. Now, supposing you're looking at a upper air map, maybe 300 millibars, which is like 30,000 feet up. And these are height lines. These are lines of equal height. And this is the way the upper atmosphere maps work, where you're measuring the height roughly above sea level of where the 300 millibar surface is. And the winds blow parallel, or at least in a balanced situation will blow parallel to these height lines. And so you notice that they're tightly packed back in here, but then they really begin to spread out in this area here. So there is definitely what we call directional divergence going on, that these winds are turning into the west and even southwest, and these ones down here out of the northwest. So they're spreading apart, okay? Now, so we definitely have diffluent flow, okay? However, is it necessarily divergent flow? Okay, so let's examine this. We have directional divergence going on there. We've already talked about that. But we have speed convergence going on because the winds blow more strongly where these height lines are tightly packed and more weakly where they're more spread apart. And so you have fast winds blowing into slower winds, and you have speed convergence. And if that balances the directional divergence, then the flow is balanced, or what we call geostrophic, and basically nothing happens, okay? So when you look at an upper air map and you see the lines spreading apart, it's tempting to think that that always means divergence, but it all has to come down to whether or not the speed convergence is balancing that, or could the speed convergence be dominating the directional divergence? So these are all things that need to be taken into account. It never is as simple as things appear. Okay, now I want to talk a little bit about how friction causes an imbalance in forces. So I should have made these arrows curve, but in the interest of time, it was easier to do this. So we all know in the northern hemisphere, the winds blow counterclockwise around an area of low pressure. And in a balanced flow, the pressure gradient force, which goes from high to low pressure, is directed in toward the low. And the Coriolis force, which is caused by the Earth's rotation, blows to the right, 90 degrees to the right of the wind. However, let's say friction comes along. Friction slows down the wind, and the Coriolis force is proportional to the speed of the wind. So if the wind goes down, the Coriolis force goes down, and now the pressure gradient force is dominating, and this turns the winds a little bit toward the left, okay? And so this is why the air spirals into the middle of a low as opposed to just circulating around it in a perfect circle. And so when it spirals in toward the center, that is convergence. And when you have low-level convergence, you have rising motion, and you get clouds of precipitation if moisture is abundant enough. And so in this case, friction, which is significant over land, really plays a role in increasing the low-level convergence, which can make it precipitate harder. Okay, last but not least, we're going to talk about something called the supergeostrophic wind and the subgeostrophic wind, okay? And it can still be balanced, but the winds are stronger in one area and weaker in another. So we're going to talk about that now. So again, we're in the upper atmosphere here, and this would be considered a trough in here. Then we've got a ridge, then we've got a trough, and then a ridge, okay? Now, up here, the pressure gradient force is going to be directed to the left of the flow, okay? But this time, because the flow is curved, we have centrifugal force as well, which always sort of tries to not make the turn, but spiral it out to the side, okay? So now you have the pressure gradient force and the centrifugal force acting in the same direction, and the Coriolis force has to balance that. And so the Coriolis force has to increase to balance these two forces that are acting against it. And we said before that the Coriolis force is proportional to the wind, so if the Coriolis force increases, the wind increases, okay? So then we have what are called supergeostrophic winds, in the ridge where the flow is curved in what we call an anticyclonic manner, which would be this area right in here, okay, and also over in here. Okay, now let's take a look at the trough area where the flow is curved cyclonically, all right? So we have the Coriolis force acting to the right, and now we have the centrifugal force acting in concert with the Coriolis force, and so the pressure gradient force now has to be greater than the Coriolis force because it is balancing two different forces. So now the Coriolis force is weaker than the pressure gradient force, and as the Coriolis force goes down, the wind goes down, okay? And so you have what we call subgeostrophic winds at the base of these troughs, okay? So why is all of this important? Well, when you have weak winds going into an area of stronger winds, you have speed divergence, okay? And so you have divergence in here and also over in here. And when you have fast winds blowing into an area of slower winds, you have speed convergence, okay? And so think about this. This is in the upper atmosphere, okay? And whatever is going on up there, it's the opposite down at the ground or in the low levels. And so if you have divergence aloft, where the air is spreading apart up here, something has to come up to replace that. And so you have rising motion, and then at the low levels you have convergence, and this is where you get clouds and precipitation. So this is why to the east of the trough axis, we get the sensible weather of clouds and showers and thunderstorms and all that type of thing. However, when you're going from the strong winds to the weak winds, then you have convergence aloft. And when the air comes together up there, then it goes down, sinking motion produces warming and drying, and then it spreads out at the ground, okay? Which would be associated with high pressure in the low levels of the atmosphere. And this is why to the left of the trough axis, you get sinking motion and usually nice weather, okay? So all of this has to do with balance of forces, the pressure gradient force, the Coriolis force, and the centrifugal force. And this flow actually is balanced, but the Coriolis force is changing magnitude depending on whether or not the centrifugal force is acting in concert with it or acting against it, okay? And so as a result, we set up these divergence, convergence patterns, which then play a significant role in what kind of weather we get. Okay, there are the credits. Hope you found that mildly interesting. That is the bonus weather video, the second one of the week. We'll have the third one of the week on Friday. The daily weather update will be coming up very, very shortly. And I hope you have a wonderful Wednesday evening, and we will talk to you again tomorrow. Take care, everybody.